Good day and welcome to this MoTeC webinar. My name is Dwayne Mitchell and I work in the MoTeC Research and Development Centre in Melbourne, Australia. And the topic for today's webinar is MoTeC ECU technical terms explained. So what we're going to do is go through a glossary of the terms most frequently used in our MoTeC ECUs. These are the sort of terms that get frequently used in conversations with our support staff, and it's quite common that the terms are used across the fuel injection world, but there are a few that are specific to MoTeC, so that's why we're going to go through all of the terms you can see on this page. Now these are all grouped into functional groups, so there aren't quite as many as you might expect, but and this is not a discussion of how our ECUs work, merely a description to help you to work through our normal operating software. So we're going to cover Refsync, Refsync capture, modes, hall sensor, magnetic sensor, rising and falling trigger, CRIP, injectors, injector drives, pulse widths, mapping systems, fuel and ignition compensations, throttle settings, lambda, boost control, and finally how our configuration files are discussed. So, firstly, Refsync. Now this is a term that gets used very often within a MoTeC environment, and it's an abbreviation for reference and sync. And these are the two sensors that are absolutely essential for the operation of an engine using one of our ECUs. Now there are some variants, but effectively you can assume that a reference sensor is the speed sensor that goes on the crankshaft. Now this is a sensor that will tell us how fast the engine is rotating. That's its principal use. And secondly, it's used for calculation of ignition advance. So this is an absolutely critical sensor for good operation. The sync sensor, or the synchronization sensor, is the second sensor that we almost always use on a four-stroke engine, and that is almost always used as a camshaft position sensor. So the objective for this sensor is to identify which of the cycles of the two engine revs is the power cycle for the cylinder 1 top dead center, and that way in the use of a sequential injection system, the ECU knows which cylinder is to be firing in which order. Now without this synchronization sensor, it's not possible to have sequential fuel injection or indeed sequential ignition. There are some modes that allow us to use reference only, but these tend to be a group fire type of situation. So that's what reference and sync sensors are. Now one of the most useful tools that you'll hear often of if you need to talk to MoTeC support is a Refsync capture. And that is a utility tool that's available in our ECU Manager program. And the objective is to actually make an oscilloscope recording, if you like, of what those signals look like. Now we've got one here on screen. It's not shown perfectly on the screen, but nonetheless what we'll see here is we've got this the yellow signal, which is fluctuating continuously up and down, and that is our reference signal in this case. And then we've got another signal here which is in green or blue, and that signal is our sync signal. So what you can see are two different voltage levels, and this capture shows the engine rotating quickly as these waves here move further apart. It's because the engine's actually slowing down when it hits compression. And then what we're seeing here is a missing tooth event, and this is one of the ways we use a reference sensor to tell us whereabouts in the rotation it is. And our second signal here, the sync signal, is basically a voltage level which at this point here is switching down to 0 volts. And then at this point here, it switches back up to a high voltage. So the point of this Refsync capture is that in one screen, we can see both of these critical sensors, and we can determine, amongst other things, what type of sensor they are. Now at the bottom of the screen, you'll see that there's a link to a webinar which will cover this topic in great detail, and many of the screens we have in this webinar have references to other webinars. So if you need to get into some proper detail on any of these terms that we're discussing, you'll find there's a webinar that's actually going to give you a great deal of information on that subject. Now, the next thing that is most frequently the cause of some confusion is what we call the Refsync mode. Now this is a combination of the ref and sig signals which describes what the actual triggering mechanism for a given engine is. Now, because we have to be able to, with our ECUs, cover a vast number of engine types with different triggering systems, that's why we have these Refsync modes. And this allows, depending on which mode is used, it allows the engine tuner to specifically configure the ECU for the triggering system that's on the engine that they're using. Now, there are many generic modes, which are the ones that you can, for example, build your own trigger plates or use existing distributor systems if you like. And these generic modes allow many common triggering systems to be used. So what we have, for example, are one tooth mode where you have one reference tooth per firing, which is an older style of triggering mode. And then we have many other modes such as multi-tooth modes where you may have, for example, 36 teeth on the crank trigger. And then we also have missing and additional tooth modes where you may have some teeth on the crankshaft and then a gap in those teeth. And once again, that helps us identify whereabouts in the engine cycle we are. So the generic modes allow you to have multiple combinations where you may have a particular type of crankshaft trigger sequence and a different type of camshaft or synchronization sequence. And we also have what we call OEM modes, or original equipment manufacturer modes. Now these are the ones that relate to particular trigger systems. They tend to be used on later type engines that have variable cam timing, because many of these engines have quite sophisticated trigger sequences on, for example, each of their camshafts, so that the ECU can identify the individual phase of each camshaft very quickly. So many of these modes are used, for example, with WRX Subarus or BMWs with the Vanos cam timing system, Ford Cosworth, Gen 3 LS type engines, Ducati engines and so forth. These all have unique triggering systems, and so MoTeC has written specific software for these systems, and that's what we call the OEM modes. So in your Refsync mode set up on the ECU Manager program, you can either use these generic modes if you have a more traditional triggering system, or you can use one of the purpose-designed OEM modes. Once again, there's a very good webinar on this topic, and if you follow the link at the bottom of the screen, you can get a great deal of information on this subject. Now, our ref and sync sensors are usually either a Hall or a magnetic sensor type. These are the two most predominant types of sensors used with our systems, and of course used on most OE systems as well. So these are the rotation sensors that are placed on the crankshaft or in the distributor body or in the cylinder head over the cams, depending on the particulars of the engine that you're using. Now the two simplest types again are the Hall type, and this is a switched sensor which uses an interrupter disc or some sort of proximity type of system on a gear, for example. And these sensors usually have three wires. They have a power supply, a ground, and a signal wire which goes to the ECU, which is the actual triggering signal. And typically what these sensors look like, they effectively act like what you might consider a set of points on an old-fashioned distributor. And that is that they switch the triggering signal to ground. So when they're plugged into an ECU like an M800, if they're not switching to ground, there's a roughly 3.5 volt voltage there, and when they hit the triggering point, for example, a gear tooth or a camshaft lobe, they will switch to ground, which means they short circuit that signal to ground. So there are only two possible voltages, 0 volts and 3.5 volts approximately. These typically have three wires, as I mentioned. Now the magnetic type of sensor is an AC variable voltage sensor, usually has basically a magnetic coil wound in it, so that when it sees varying magnetic levels or flux, it produces a varying AC voltage. So these typically have two signal wires, and that would be the 0 volt wire and the signal wire. And in some cases they have three wires where they have a separate ground. This gives better noise immunity, but they still produce an AC variable voltage. Now this voltage, because it's generated from a magnetic source, it varies with speed. As the engine speed goes up, the voltage of this sensor changes as well. So they're the two most commonly used sensor types, and these are the ones that you need to set up in your reference and sync settings on the ECU. Now, another term that's associated with these ref and sync sensors is rise trigger and fall trigger. Once again, when you're setting these in your ECU manager program, you need to establish the direction of voltage travel, which is the one you're looking for to produce accurate timing. So, in particular with magnetic sensors, you can see in our display below on the bottom of this screen, we have two different triggers. Basically, this one here shows us the voltage as it fluctuates here at 0 volts. When it sees a magnetic lump, it goes low, and then it passes through 0 volts again, and this is our trigger point. And this is again what we would call a rising trigger, as this voltage goes in a positive direction from low to high, and then back to 0 volts here. Falling trigger is obviously the opposite of that. So we have 0 volts, we see a high voltage being generated, and then this voltage quickly passes through 0 volts and down into a negative voltage, and that's a falling edge there. And once again, this is the critical point for example, for ignition timing. So this is what we would call a falling edge trigger. And again, these need to be selected correctly, or else you'll have ignition timing errors amongst other things. Okay, now one of the terms that gives people a great deal of grief with our ECUs is the CRIP, which is the Crank Reference Index Position. Now this is a number which describes the number of degrees between a particular tooth on the reference sensor and top dead center of cylinder 1 on compression. Now, so in other words, this number could be anywhere from 0 to 720 depending on the nature of the engine and the nature of the triggering system. And it is absolutely essential that this number is correctly set so that the ECU triggers each ignition coil at the appropriate time. Of course, if this number is wrong, your ignition timing will be wrong as well. So again, we're not going to go into detail about how to do this. Simply the term CRIP, or Crank Reference Index Position, is one that is essential for correct ignition timing, and it varies depending on which Refsync mode is in use. We have a very good webinar on this topic, and if you are suffering from some confusion here, I suggest you take a look at that webinar. Okay, now quickly we'll look at injectors. There are basically two types of injectors that we can deal with: high ohm injectors and low ohm injectors. So all we're describing here is the DC resistance of the injector. Now it's important here to get this correct because in particular with low ohm injectors, you can damage or destroy these injectors if you don't have the right settings in your ECU. High ohm injectors are the older style of injector. They generally measure about 10 to 18 ohms of resistance, and they use a relatively low amount of current, say about 1 amp of current. These are very common on the earlier generation car engines, and they're still used on many modern car engines and also a great deal of motorcycle and PWC type engines. These injectors were less accurate in the past. As time has progressed, they are now actually fairly accurate, quite accurate and quite usable in modern applications. They tend to open a little bit slower, and that means that they can make it difficult to map the low load areas of an engine, particularly if you're using very high flow injectors. So these were the reasons initially that the low ohm injectors were developed. And what a low ohm injector is, as you can see from this picture, they are the type, this one here is the what we call ID1000 injectors, but they're very similar to the Bosch EV12s or the Siemens Decker injectors. The one above, the high ohm injector, that would be more typically called a Bosch EV1 or EV6 injector. So low ohm injectors generally have a measured resistance of only about 0.5 to 8 ohms, which means they pull much more current if they are left simply switched on. Generally that means they turn on much faster than a low ohm injector, and they can give much more precise control. They also unfortunately require more sophisticated electronics. But so that's the difference between a high ohm and a low ohm injector. Now associated with high ohm and low ohm injectors is the electrical drive mechanism which allows proper control of these injectors. So a low ohm injector uses what we call a high ohm injector uses what we call saturated drive, and this is because they have relatively high resistance and you simply need to turn the power on and off for these injectors to function. So on the little graph below, on the right hand side, we can see our high resistance injector, our high ohm injector, and all we're doing is grounding one side of this injector, as you can see, and the time that from this edge to this edge is how long the injector is turned on. And during that time, all we need to do is switch it to ground. The current here will build up slowly, and then it will basically find a point at which no more current flows, which is what we call saturation. So a high ohm injector has a very simple control strategy, and there's no downside here apart from the fact that they can take longer to open and they may offer less reliability, less precision. Now, the other type of control mechanism we use is called peak and hold drive, and this is what we need to use for a low ohm or low resistance injector. So this is our drawing on the left hand side, and what we see here is there are two stages to this type of control. The first stage, we simply turn the injector on as we would have done with a high resistance injector, and what happens here, as you can see from this current trace below, is in fact a lot more current flows because these injectors are lower resistance. And so then we reach a point here which is what we call the peak current, and then the ECU reduces the amount of current control and allows the injector to hold a lower current, which may be somewhere, say, like 1 amp, whereas the peak current may be something like 4 or 5 amps. And the idea here is that it takes this high current to open the injector because it's got very low resistance. Once the injector is open, we can just hold it open with this lower current. So the point here is that if you happen to switch one of these injectors on permanently, they will basically blow up because the current will just keep increasing here because of their low resistance. So a peak hold type of drive is required for any low ohm or low resistance injector. All right, now another term that sometimes two terms that get a little bit confused with each other, pulse width and duty cycle. So this is in particular referring to injector times, and the pulse width is simply the amount of time that the injector is held open. So this is usually discussed in milliseconds, which are 1/1000th of a second. Sometimes it's discussed in microseconds, which are millionths of a second. But normally we would say we have, say, an injector pulse width of maybe 4 milliseconds or 2.5 milliseconds. So that's 4/1000th of a second. And you can see here what we have is our pulse width, which is the time from the switching on point to the switching off point, and that pulse width is that is the duration of the injector pulse. Now, duty cycle is a ratio which determines of the available time how much of the time the injector is turned on. So this relates to what the overall cycle time is, and the cycle time depends on what their engine RPM is. So here, for example, we turn an injector on once per power cycle, which is once for every 2 engine RPM. So the cycle time starts here and it finishes here. Now the injector is turned on for some or all of this time, and that is the term that we call duty cycle. That is how much of the available cycle time the injector is turned on for. So a good example, as you can see from this little graph, the pulse width time here is, in this case, we would say it's about 9/10ths of the overall cycle time, and that means we have a duty cycle of roughly 90%. Okay, so the point about duty cycle is that as the engine spins faster and faster, there's less cycle time available, and ultimately there's the same amount of overall time available because once the injector is turned on continuously, it is maximum flow regardless of the engine speed. But what you need to consider is as the engine speed goes up and the requirement for fuel increases, if we're turning the injector for longer amounts of time, our pulse width is longer, eventually it will become close to or equal to the cycle time, and therefore our duty cycle will be 100%. And at that stage, the only way to get more fuel delivery is to use a different injector with higher flow or to increase the fuel pressure. So that's why the term duty cycle is critical. When we approach, say, 90 to 95% duty cycle, what it means is we are running out of available fuel, and from that point on we may see leaner mixtures than we need. Okay, now another couple of terms that are used somewhat confusing to people with our ECU mapping is efficiency method and load method. Now, you don't actually need to pay a lot of attention to these once you've set up your basic start files. but the point here is that we describe the efficiency method. This is the selector for which input signal is used on the vertical axis of the fuel map. Now, typically we may have throttle position, manifold pressure, or mass airflow. They are the most normal vertical inputs. In other words, they're how much engine load or how much engine power we're trying to generate at a given RPM. So that is what we call the efficiency method. Now, secondly is the load method, and this is exactly the same thing, but it refers to the ignition map instead of the fuel map. So in your ECU setup table, you'll find that there is two parameters you need to set: efficiency method and load method. In most cases, they are set to the same input, for example, throttle position on a naturally aspirated engine or manifold pressure on a boosted engine. Now, on our two examples on the right, you can see an ignition map that shows load in kPa, and that clearly identifies it as a manifold pressure type of map, and we're looking at load levels from 30 to 100 kPa. So it's basically a naturally aspirated manifold pressure type of ignition map. Same thing applies on our fuel map above. The efficiency is specified here in kPa, and once again that indicates a naturally aspirated engine. Now, for example, if we had selected throttle position here, what our efficiency would be simply percentage of throttle, and would typically go from 0% to 100%. Okay, now compensations, this is another term that comes up frequently, and it gets used in many different parts of the ECU's operation. Compensations are basically tables which make adjustments or corrections to our basic parameters such as fuel timing, pulse width and ignition timing. So these are normally designed to allow for things like engine temperature or air pressure or battery supply voltage, which affect the way the engine is going to behave, and therefore we need some more complexity rather than just the basic fuel or ignition table. So the compensations are all applied to either the fuel or ignition or some of our other parameters, and they allow us to compensate for things like engine temperature. Now, typically fuel compensations are shown in percentage trims, and you can see in the example we have here, we have a fuel engine temperature compensation here. It's a percentage trim, and at a given engine temperature, say 20 degrees, then what we have is a 35% trim. That means the number that comes from the base fuel map is made 35% larger, and that means more fuel, of course, will flow. Once we get into the higher engine temperatures, for example, here at 80 degrees, typically we have zero trim. So these are percentage trims. Now, ignition compensations are usually in the form of timing rather than percentage. It's certainly easier to understand. So in our example below, we have, this is an ignition trim for air temperature, and that means that, for example, at, say, 80 degrees of air temperature, we have 6 degrees less ignition advance. Now, you'll see here we actually have an extra axis on our table, and that's a load axis. Once again, this relates to manifold pressure, and that means at lower, for example, idle throttle, at very high air temperatures, we might retard the engine by 6 degrees, and then at full throttle at 100 kPa, we might take out 10 degrees. So this is a protection mechanism. Again, this allows us to build a complicated adjustment or correction or compensation for different factors that may affect the overall ignition timing or the overall fuel pulse width. Now, there's a question here that are the compensations always for temperature? And the answer is no, they can be for many things. For example, air pressure or battery voltage. We're just using air temperature as an example here. But depending on what it is you're making compensations for, there can be compensations for all sorts of things. Indeed, you can have boost compensations. There are almost unlimited number of possibilities. And indeed, one of the other compensations we have is battery compensation. Now, this is a slightly different version of a compensation because it's applied to the fuel pulse width, but rather than being a percentage trim, it's an additive trim, and that means that the value is added to the fuel value. Battery compensation, or battery comp, is another setting that we use to adjust for injectors. Slower injectors take longer to open, and especially as the lower battery voltage comes, then it may be necessary to add extra time so that the number in the fuel map produces the same mixture regardless of the battery voltage. So this is typically used for battery compensation, is used to allow, for example, the high ohm injectors, which take quite a lot longer. And in this case, at 8 volts, we can see that it's adding actually 2.5 milliseconds or 2,500 microseconds. So that's a significant amount of time. Dwell is a similar compensation that we apply to ignition coils. Normally, ignition coils, say at an operating voltage of 14 volts, they will saturate quickly and therefore produce maximum ignition energy. If your battery voltage is lower, which is typically, for example, when you're cranking the engine, we still need to get the same amount of ignition energy, and therefore what we do is we turn the coil on for a longer amount of time, which allows it to still achieve saturation. Now, this is something that many people misunderstand with ignition coils. A given ignition coil with a normal, say, 12-volt supply can achieve saturation in a short amount of time and deliver a certain amount of energy. Now, the same ignition coil can produce the same amount of energy, even from a lower voltage, as long as it has sufficient time to reach that saturation point. So here we have a compensation table that shows, for a given battery voltage, how many milliseconds of time it takes for this given ignition coil to achieve that saturation. Once again, the objective here is to get the same amount of spark energy regardless of the battery voltage. Now, most of our systems use throttle position as a primary input, for example, in the fuel map. And the other thing we often have is drive-by-wire or electronic throttle systems. These are systems where the individual throttle body on a given engine may have slightly different position or slightly different voltage levels from fully open to fully shut. And so normally we have we make a unique calibration for each individual engine, so that when you place a configuration into this engine, you need to set the throttle high and throttle low for that exact throttle body. In some cases, even changing the throttle position sensor means you should reset these numbers. Now, this is important so that your fuel maps and your spark maps actually track correctly when you change things like sensors. So all we're doing here with throttle high and throttle low is we're defining the raw voltage level from the throttle sensor, and then the ECU calculates from 0 to 100% once these two voltage levels have been set. So that's done as a live connection to the ECU. You simply have to fully shut the throttle and then press the relevant key, and then you fully open the throttle and set it to the other position, which is throttle position open. And then once it has these two voltage levels, it can calculate from 0 to 100% throttle. Now, simple throttle systems only have the two values, throttle high, throttle low. Most electronic systems, for example, drive-by-wire, they have a number of extra inputs because we're looking for safety. We want to make sure that nothing misbehaves. So typically, drive-by-wire systems have a main voltage level for the throttle position, and they have a second tracking level as well. So that means we have to set throttle position high and low for both of those sensors. In the ECU manager, it's called throttle position and throttle position 2. And then we also have normally what we call a driver pedal or a driver throttle, which is the electronic pedal that replaces the throttle cable. And that also has two sensors on it, so therefore we have to set a closed and open level for each of those. So in a typical drive-by-wire system, we actually have 8 levels that need to be defined. So that's another thing that's frequently a cause of misunderstanding with our customers. And if these settings aren't properly done when an engine is first used, you'll get a lot of grief later down the track when you're trying to tune the engine and these figures aren't properly set. Okay, now another term which causes a great deal of confusion is lambda. This is often interchanged with the AirFuel ratio. These terms are not actually the same thing. They're two different terms, and so we're going to explain what the difference is. Now, AirFuel ratio is simply a mixture of a measurement of fuel mixture or richness, which is used in virtually all engine tuning. AirFuel ratio simply describes the relationship between the amount of air and the amount of fuel in our mixture. So an AirFuel ratio of 14.7 to 1 would mean that we have 14.7 grams of air for every gram of fuel. So that AirFuel ratio is an indication again of what the mixture is. Now 14.7 to 1 is what we call stoichiometric, and that is what we have a mixture required for perfect combustion. It doesn't actually produce the best power, and that's why we need to be able to measure different air-fuel ratios. So if we're looking for a richer air-fuel ratio, what that means is we have less air for the same amount of fuel, and a typical number would be something like 12.5 to 1. And if we're looking for a leaner air-fuel ratio, what that means is we have more air for the same amount of fuel, and another number you might see there is something like 18 to 1. Okay, so these have to be seen relative to that number of 14.7 to 1, which is the stoichiometric number, which is the air-fuel ratio that produces what they call ideal or perfect combustion. Okay, now the reason that we also have the term lambda is that the air-fuel ratio, in this case I've used the air-fuel ratio of 14.7 to 1, which is the ratio we use for petrol. However, different fuels have different air-fuel ratios to produce this same stoichiometric ratio, and therefore it can be a cause of some considerable confusion if you change fuel types. And a great example of this is running from normal unleaded fuel, gasoline, to, for example, E10 or E85, which is an ethanol blend. Now these E10 and E85 fuels have a different air-fuel ratio for stoichiometry, which means that the number you might use for your ideal full power type air-fuel ratio is going to change. So the reason air-fuel ratio is a term that we try to avoid here at MoTeC is so that we can go from one fuel type to another and still have numbers that make sense. And the term we use is lambda, and this is virtually a descriptive term for the air-fuel ratio, and it is independent of the fuel type. So an air-fuel ratio of 14.7 to 1 for petrol, or the stoichiometric air-fuel ratio for petrol, we express that as lambda 1.0. Now, a different fuel, for example, E85 has a different air-fuel ratio, but when it is at that stoichiometric ratio, it would still be a lambda of 1. So the benefit here is that if we're looking for a richer lambda, we have a lower number, for example, a lambda of 0.85, and this would be a typical number you would use in some power settings on some engines, and this may be across different types of fuel, as a matter of fact. And a leaner lambda would be a higher number, for example, 1.25. And again, the reason MoTeC uses the term lambda in preference to air-fuel ratio, again, they both describe almost the same thing, but air-fuel ratio is particular for the fuel type, and lambda is not particular for the fuel type. Right, now lambda sensors are another cause of a great deal of confusion. Many road cars have lambda sensors installed as a standard part, but in many cases the type of sensor they use is not suitable for performance tuning. Typically they have what we call a narrowband lambda sensor, and the objective here is merely to measure the stoichiometric ratio and nothing else. Now, a narrowband sensor is often used in road cars to achieve emissions standards and to make compliance, in other words, but they're not a suitable tool to be used for performance tuning. So the other option is what we call a wideband sensor, and this is a sensor that has a greater range of measurement rather than just simply that stoichiometric ratio or that air-fuel ratio of 14.7. And wideband sensors are the ones we typically use for tuning of race engines, anything that's critical. In fact, some later model cars now have a wideband sensor before the catalyzer, and therefore it's a little bit easier for us to plug into these cars because we already have access to these sensors. Typical wideband types would be the NTK L1H1, the Bosch LSU 4.0, the Bosch LSU 4.2, and the Bosch LSU 4.9. Now these are all sensors that we sell here at MoTeC, and in fact all of our 100 series and M84 ECUs can connect directly to these wideband sensors. And there's a photograph there, I think that would be an LSU 4.9. So that's the particular thing about lambda sensors. Just to reiterate, narrowband sensors, although they're very common on OEM vehicles, are not particularly useful for the sort of tuning that you would require. Now we have a very good webinar on this topic, and there's a link to that at the bottom of this page. Okay, so within our ECUs we have a lambda input, or we may have a lambda input, and the nature of tuning an engine is that we require different lambda or different air-fuel ratios for different load conditions. Now the reason for this is firstly that allows us to achieve better fuel economy, lower emissions, but it also allows us to achieve better power and better acceleration in the areas where this is critical. So typically the Lambda that we need for this, we have a table in our ECU manager that allows us to predefine which Lambda levels we're looking for, and this table can be used in a number of different ways. So that's what we call a Lambda Aim, or the Aim Lambda table, and that's in our ECU manager program. So we can use this table either in our quick tuning mechanisms or in our Lambda WAS mechanisms, and also if we have closed loop Lambda modes, then this table is used for actual live control. So the Lambda Aim is something that the tuner can set. It may or may not directly affect how the engine runs, depending on which Lambda control mode you're using within the ECU. As a rule, the start files or the configuration files that we distribute have fairly conservative figures here. We're looking for safe engine operation, and everybody who operates especially boosted engines may go for far more dramatic Lambda numbers, but the point here is to achieve maximum safety and achieve the best power and the best efficiency at the same time. Okay, now one of the other facilities we have with our ECUs is to have boost control, and these again are terms that are used quite a lot within the MoTeC environment. Now normally boosted engines can have electronic controls which allow you to get specific boost for a given RPM or load conditions. Supercharged engines you can't normally do this with, because most supercharged engines simply have a supercharger that's driven at a speed relative to the crankshaft speed. So boost pressure is really just a function of the speed of the engine. It's not so easy to control how these work. Turbocharged engines, on the other hand, frequently have electronic control of the wastegate. Normally we use a solenoid valve in the wastegate circuitry, and what that means is that the natural boost limit of the wastegate can be changed and higher boost can be achieved. So the solenoid valve is controlled normally by either an open loop or a closed loop control system within the ECU, and open loop systems are often quite adequate to do this. And what that simply means is for a given engine load or RPM, we put out a duty cycle, a pulse width modulated duty cycle, which controls that solenoid valve and achieves the required amount of boost. The other option is to control it closed loop, and in this case what we use is what we call PID, which is a control algorithm, and in this case we use a boost aim table, and the objective here is, rather than specifying the amount of duty cycle for a given RPM, which may produce varying amounts of boost, we put in a boost aim table which tells us what the target amount of boost is, and then the PID mechanism allows us to achieve that value. So that introduces this term of PID, with PID control, and that is proportional integral derivative control. So this is a closed loop automated system where we simply specify the amount of pressure, boost pressure we're after, and the ECU controls the solenoid valve to achieve that pressure. Now PID tuning is quite a complicated topic, and the values are tuned to allow for example, the delays in turbo systems and for variations in boost wastegate and so forth. So what you're doing is tuning the PID system to accommodate the mechanical variations in the engine, if you like. Now these are both very complicated topics, and there are in fact two webinars that you may find useful. One of them is on PID parameters and the other one is on boost control setup. Okay, now the last thing we're going to look at is the configuration file. Once again, this is a term that you're going to strike frequently when you're dealing with MoTeC staff, and simply what that is it's the description we use for the tune file, which contains all of the settings and all of the maps for a given engine, or in this case for a given product. So all of our MoTeC ECUs, M800s and M84s and so forth, they all use a configuration file, and that file tells them all of the things we've just been discussing: the Refsync mode, the injector duty cycles, the maps, the corrections. All of this information is contained in this one file. Clearly a very useful way to exchange the information. And the reason it's useful is because these files are always stored in the same directory on a given PC. And for example, our M800 configuration files are stored in the directory C/MoTeC/M800-V35. Now the reason this is useful is that It's very helpful to the MoTeC staff here in our support department. If you need help, you can simply email this file. It's quite simple to detach this file, send it as an email, and then we can look at exactly how you've set your engine up. So the configuration file, or what we normally just call the config file, is an absolutely essential part of how our systems work, and it contains everything that we need to know what you've done with your engine and how it's working. Once again, there's a very good webinar on this topic, so if you need help on how to email these to a MoTeC person, then just have a look at that webinar. Okay, now we're not going to go into detail on communications terms, but these are some of the terms that you're frequently going to come into contact with whilst you're dealing with MoTeC. Now, firstly, we have a number of different communication standards. USB, which is Universal Serial Bus. This is the one that's frequently seen on most laptops these days. It's the small rectangular 4-pin. Okay, CAN is Controller Area Network. Once again, this is the communication system used on many vehicle systems. Most of our ECUs have CAN and our dashes and so forth, and it's an intercommunication bus between multiple devices, usually within an automotive environment. Now, Ethernet is another communications mechanism. Local area network cables are those blue cables with the 8-pin plugs, and some of the later MoTeC devices have Ethernet as their communications method to the laptop. RS-232 is an older serial communications standard. It involves a transmit wire and a separate receive wire, and that's the older 9-pin D-style connector that you would see on older legacy type of PCs. Not frequently seen on the current generation of PCs, but some of our ECUs still have RS-232 capabilities as well. The thing that you will see RS-232 on at the moment are GPS receivers. Virtually all GPS receivers have an RS-232 output, and that's how our ECUs and dashboards collect GPS information. Now, K-line is a automotive interconnect bus. This is a single wire usually, and this is used on Japanese vehicles, but it's used in European systems as well. And K-line is used predominantly for diagnostic messaging rather than for high-speed engine messaging. But one thing that it gets used a lot in is dashboard communications, and many current vehicle systems use it for lower speed communication between an ECU and the dashboard. Custom data sets. Now, these are generally relate to CAN data sets or controller area network data sets, and these are the data sets that are specified in our ECU manager for us to generate a particular CAN messaging. So a custom data set can be set up in an ECU manager program, and then it can be stored as a CAN template, and this can be used in other MoTeC devices such as an ADL dash logger. Telemetry is a form of shifting data remotely, therefore without the use of cables, and MoTeC has a number of telemetry systems which either use older-fashioned radio transmitters at a fixed frequency or the current spread spectrum type radio transmitters, and the other thing we can now use is GSM telephones or GSM radio transmitters. So telemetry is a means of seeing the data on the vehicle without being attached to the vehicle. Finally, driver. Now, we're not referring here to the driver of the vehicle. We're referring to the software drivers that are used, for example, for our MoTeC UTC devices. So you'll see this term quite often. And there are some situations where if you cannot connect to a MoTeC ECU, it's because there's a driver issue with your laptop. So if you're talking to support staff and they tell you to reinstall the driver, that's what they're referring to. All right, now that's our description of the MoTeC technical terms regarding ECUs. Thank you very much for attending. Now we do have other webinars, as I've referred to throughout this one, and those links are on those pages. You can scroll back through those pages. And also we have our web forums, very useful way to get in touch with other MoTeC users, and also very useful to get help directly from MoTeC staff because we have a constant presence on these webinars as well. Thanks again for attending. Hope this has been of some help to you.